Ladies and gentlemen, a very good afternoon to each and every one of you. I hope you all are enjoying the enriching session we have so far in this FDP. It is a great pleasure and excitement to welcome our speaker of Day 6, Session 10, which have an illustrious career marked by achievements and passion for research and teaching. Dr. Mahesh Kumar embodies the spirit of research excellence. Dr. Mahesh Kumar is an associate professor at IIT Jodhpur. Dr. Kumar has received M.Tech degree in solid state materials from IIT Delhi and PhD degree in engineering from ISC Bangalore, India. He worked at Central Research Laboratory of Bharat Electronics Limited, Bangalore, as scientist from 2005 to 2013. He has received INSA Medal for Young Scientist 2014 by Indian National Science Academy, the MRSI Medal 2016 by Material Research Society of India, DAE Young Achiever Award 2016 by BRNS Research Excellence Award 2020 by IIT Jodhpur, and Friedrich Bessel Research Prize by Alexander von Humboldt Foundation, Germany. He is recipient of the Fulbright Nehru Academic and Professional Excellence Fellowship 2021 to work at MIT, USA, the Royal Society International Exchange Award, Nagasaki University, Japan, Visiting Scientist Fellowship 2021 by Chinese Academy of Science to work at Hefei Institute of Physical Science, China, Duo India Professor Fellowship 2018 to work at South Dakota State University, USA, and many more. He is also a editorial board member of IEEE Censors Journal and Nano Express. He is a fellow of Royal Society of Chemistry. He is founding member of served as chair of Indian National Young Academy of Science. Dr. Kumar is a member of Program Advisory Committee PAC of SERB and DST. He has published more than 170 research articles with the total citation of 4,985. His research interests are focused on 2D materials, nanomaterials, sensors, semiconductor materials, and devices. So without further ado, please join me in welcoming our distinguished speaker, Dr. Mahesh Kumar. Sir.
Yeah, good afternoon. Can you hear me? Last row? Okay. So today I am going to talk about the 2D materials. This one, how we can use 2D materials here for making the sensors, this one. So here I am going to talk about the this one high electron mobility transistors. This is made by the aluminum, gallium nitride and gallium nitride heterojunctions. So what is the advantage of this one transistor based sensors and how we can make for the different this one heavy metal ions detection. So all we have seen in the water purifier, basically we have the filter that is based on the time, but we cannot see the live this one how much percentage of these heavy metals are present, because these heavy metals are toxic in nature. So here briefly I am going to this one discuss about my research areas. Mainly my research is based on the material synthesis, where we are synthesizing the different type of the materials. We are working on the 2D materials, we are working on the metal oxides, and also we are working on the 3-5 semiconductors, aluminum, gallium nitride and gallium nitride here. 3-5 semiconductors, and we are using for the different applications, including the gas sensors, heavy metal ion sensors, radiation sensors, photodetectors, and memristors. And today my talk is that mainly that is focused on the 3-5 semiconductors. By using this HEMT, how we can make the heavy metal ion sensors. And briefly I will talk about the this one gauge sensors. Okay, one material aspect is there, how to make the gauge sensors, but how we can apply the artificial intelligence, basically AI, in the data analysis to get the more accurate data, because sensing is the material part is there, but again the selectivity, how we can get the better decision by using the AI. So that part I am going to discuss this one briefly here. So all we know this one, water is the important basically element for human body, and here basically we have in the different parts of the body the different concentration. So water here, yeah, here I think I can speak this one. Audio. Yeah. So basically, how to make sure this one, our whatever water we are drinking, that is the pure water. This one. So today we buy whenever we travel or when we buy this one, just we believe on the brand. Okay, this one is from Bisleri or some other brand. This water is the this one purified. This one. But how to, if we have some sensor where we can detect this one, because how to check the reliability this one, okay, whatever company they are packing this one, is this water is the drinkable here. How to make this one? So in last few years, basically water quality has degraded basically, and the main basically here source for this water pollutant is the human. Basically, we throw this one steps in the water, and because of this one, the surface water is there. This one is contaminated. This one, whatever in the water we are throwing, for example, in the lake water or river water, and then this mix with the groundwater and destroys the complete. And this destroyed the complete basically water resources, this one. And where we are using this one heavy metals basically, so this water pollution we can divide broadly in the three areas, and mainly the main here pollutant is there. These are the heavy metals. We are using the lead, mercury, and these ions basically. Here arsenic in the West Bengal basically, there is a arsenic basically in the basically large quantity this one. So how to detect whatever we are drinking, that water is the drinkable is there. And today we are using, for example, lead we are using in the textile industry, also in the agriculture, pesticide we use the basically different basically here heavy metals, this one, mercury we use this one. And now what is happening with the rainwater or other this one, this is coming basically in the our water sources this one, and making the contaminated water. So whatever our water supply is there, particularly here either from the groundwater or we are getting through the basically here river this one. So this water, how to make sure this one here this water is not contaminated here. And if we talk about the recent news in the different media, this one, Chambal here, basically this Yamuna river water is there. This is already basically this one highly toxic with the heavy metals. Again, in the different part of the country, basically here this one in the Chambal, in the Yamuna, Ganga, everywhere basically we throw, and because of this one, water is the totally contaminated this one. Today, how we are measuring this one? Suppose if you order a water purifier, this one, here the agent will come and he will measure the TDS. What is the TDS? Basically, he measures the conductivity of the water, how much conductivity is there. But in the heavy metals here, because there is a very small change in the conductivity. If lead is mixed or mercury is here mixed in the water, here the change in the conductivity is almost negligible. But if this is in high concentration, it's highly toxic for the human health, this one. And when we are measuring the TDS, this is the groundwater quality is there. Already this Rajasthan is basically TDS is also very high, this one, particularly here in this region. And when TDS is high, and again, these heavy metals are mixed with this drinking water, this one, then this is the danger for the health. So these are the basically WHO defined limits. For example, Hg should be the less than this one around 1 ppb, cadmium should be 3 ppb. So in the small quantity also these are highly toxic. But same time we need also some basically some heavy metals, for example zinc, iron, silver. This in a small quantity, these are essential for the human body. And during the COVID basically, here doctors they have suggested the zinc tablet. So that is the necessary this one. So how to detect this one? For example, here our water purifier is there. If you can get one display, how much different these heavy metals are there, how much TDS is there, that will make the more reliability, because today in every house basically we are using the water purifier. Why these companies are not making? Again, if Yamuna river, if this here lead or heavy metals ions, these concentration is increasing, we need basically, government need basically some online measurement system. In the laboratory we can measure, every time we have to collect the sample and then we have to measure. But in online, if you can basically install these sensors, and wherever basically this water level is increasing, we can get the some alarm. Now, from the government side, there is a basically restriction when this textile industry or some other industries, when they release the water, they should purify the water. But when they are doing purification, because cost is involved, so to save some money, basically this one release the water without purifying, and government cannot monitor, because who is the government? We are the government basically. So we need some system that we can basically detect this one whenever this ion concentration is high. We are measuring in the TDS only the conductivity, this one, and already we know this one, particularly in part here, this TDS level is very high, this one. So here conductivity is not the criteria, this one. By using this one, we can detect this one. So we have to make a device, and that device should, any sensor, if you are making the gas sensor, water sensor, or any other sensor, these are the basic characteristics basically here. For example, here cost is very important, cost should be low. Again, the selectivity, cross selectivity, fast response. For example, you are measuring for mercury, and your lead is also basically sensed by the same device, this one. So this is called the cross selectivity basically. So whatever our device is there, that should sense only the particular targeted ion, not the other ions here. So these are the basically characteristics. When we design a new sensor, we have to see all these aspects basically. Okay, ICP is there, we can measure by the ICP, we can get this one, but ICP cost is around 30 lakh rupees, so we cannot afford basically, because our water purifier cost is 15 to 20,000, this one. So we need, suppose we are spending 20,000, 200 rupees also additional, we can spend to see actual how much percentage of these heavy metals are present. So now I will come on the basically the technical part is the physical phenomena or chemical phenomena here. By using these phenomena, we can make the sensors, because basic concept is always same, this one. But how to use this basic concept, and then we have to make the sensors, this one, because any device or any sensor you are making, this one, we have to use the some fundamental concepts to make these sensors. So currently we have the electrochemical, we have the biochemical or colorimetry, but these methods basically we cannot do the online monitoring. Another, these are the this one tedious methods in the, because we have to mix and then how color is changing, we have to find out this one. But if we can get something semiconductor based, this one, we can do the online monitoring, this one. So in the semiconductor based, we know basically here your field effect transistor or high electron mobility transistor concept is same basically. By the voltage what we are doing, we are controlling the current between source and drain here. And now suppose here if some ions are coming, this one, that means here your gate voltage is there, here this potential is created by the ions here. And when we create basically potential here by the ions here, we can monitor the current. So in technical discussion, technical problem. So So we use the same field effect transistors concept, this one. In the field effect transistors, what we are doing, on the gate we are applying the biasing, and then we can basically, we can monitor the current here, how much current change is there between source and drain. So here we will use the same concept here. Concept is the same here. So what is happening when we are using the silicon based here, now here is the your source and drain is there, this one, and now here we are making the our dielectrics basically, SiO2, and on the top we have the gate basically metals, and now here one channel is forming, and now this current we are controlling by the gate bias here. So in this case what we are doing here, here because this current is depending on the how much bias we are applying. In the field effect transistors, this one, you have studies this one between the source and drain, how this current is changing. So what we are doing here, if I put some charges on this one, what I am doing, by this one I am applying some bias, either positive or negative. So I am putting some charges here, created some potential, and because of this potential, this current is there, your ID current is there, that one is controlled by the gate voltage. So in this case, what we are doing here, we are applying, we are bringing the ions. So if you bring, for example, mercury ions here, what we are doing, similar to the gate basically, we are creating the potential. And when we create the potential, this current will change. And this change in the current is depending on the here voltage, how much voltage we have applied. Yeah, thank you. So here you can see basically in this case particularly here we need some functionalizing materials, because otherwise if any type of ion will come basically, what will happen, this current will change. To make the selective this one, we need some selective material that can attract only the targeted ions here. For example, if you are making for mercury, if you are making for lead, if you are making for arsenic, this one, we can make basically here targeted particularly. And we are trying this one similar to the glucometer. Today, this one, diabetes patient, basically they can check how much their sugar level is there at home here. So similarly, if we can prepare the small device where we can put the water drop and we can check this one, how much percentage of these heavy metals are present, is this water is drinkable or not drinkable, this one. So we can verify. Same this device we can use in the water purifier, and we can check particularly is water is drinkable or not drinkable. So now I will come on the 2D materials. We have used this two-dimensional materials. So I think here, student, you know this one because three-dimensional material is there. And if you are making the 2D, these are the nano sheets basically. That means in one direction, your confinement is there. Carriers can move only in two directions, not in three directions. So that we call the basically 2D materials. And their properties are superior than the three-dimensional material. And the best example is the graphene is there. So here, what is the general concept and what is the quantum here, this concept basically. General concept is that if we reduce the dimension, basically mobility is low. That's why criminals we are putting in the jail, because we are reducing their mobility. And during the COVID time, we were locked in the home because mobility is less. So this is the general concept, classical concept is that if you reduce the dimension, mobility is basically low. But here in electronic concept is different basically. When we are reducing this one, here dimension, in that case mobility is high here because of the quantum confinement. Now here carriers, they know in which direction they have to move basically, and because of this one their mobility is high. And the best example is the graphene. If we take the carbon, 3D carbon, mobility is very low. But if we take only single layer of carbon, that is called the graphene, mobility is very high, this one. So in that case here, we can use these 2D materials. And if mobility is high, what will happen? Device speed is decided by the mobility. If mobility is high, device, basically your sensor, or if you are making transistor, that is the fast here. So that's why basically if we make the here devices based on the graphene, these transistors speed will be very high. So one thing is that if we take some material that mobility is high, basically we can make the faster sensors. That means immediately when these ions are coming, immediately our sensor will give the response, this one. But if mobility is low, again sensor processing time will take place, this one. So this is the first advantage. If we use these 2D materials, we can, this one, improve the speed of the devices, we can make the faster devices. And here you can see this is the bulk material is there. So how this one carrier movement is there, there are lot of scattering is involved. So how basically your carriers are moving, this one. So if scattering is more, mobility is low, this one. And another here, particularly in this case, because this path is defined, so mobility is high, this one. So this is similar. For example, from here to you are going to Delhi, one by road you are going, that means path is defined. One, if you don't have the road, you go the randomly, this one, you don't know in which direction you are going, so scattering is more, this one. So particularly in this case here, mobility is high. Now another advantage is there. Here we can, this one, understand this one. Here the sensing response is that basically is higher in 2D materials as compared to the bulk. So we can take, this is the conventional field effect transistor is there. So in that case, the channel is forming. This one is the thick channel is there in this case. So we can consider this one is the bulk material. So suppose this one is the our sensing ion is there. Now if this ion is coming near to this one, maximum impact is here on the top layers, because in our materials also there are the different layers are there. So when we are heating or something is coming near to this one, maximum interaction is only with the top layers. When interaction is with top layers, carriers can go from this side. Okay, suppose your father is sitting at the home, you can go through the another door. You cannot go out this one without any work. Here is also happening the same, this one, because here the impact is only on the top basically. And when impact is on the top, you can go from the bottom side. Some deflection is there. And what is this deflection? This one is the change in the resistance basically. Resistance, current, whatever electrical, this one property we are measuring this one. So in this case, impact is only top, this one. Here suppose this carrier electrons, these are captured by this one. Now electrons will start moving from this direction. So how sensing is happening, this one, either in gas sensor or in metal sensors, this one. This is the concept is same. If you are using the bulk materials, carriers will go from the bottom and there will be a deflection. That means there will be a change in the resistance here, but you will get the less. But if you are using the 2D materials, so 2D materials, when we are using, the impact is highest, because here we have one layer or few mono layers, this one. So impact is high. If impact is high, basically we get the maximum change. That means you are going out or you are not going out, this one. So we get the maximum change. And 2D materials, one I said basically you can grow basically one mono layers and then you can make the 2D materials. But in few materials, basically one is the gallium arsenide and aluminum gallium arsenide. Another one is the gallium nitride and aluminum gallium nitride. In between, when we are growing epitaxially this aluminum gallium nitride on the gallium nitride, because of the band alignment, here one 2D electron gas is forming. So here electrons are there. These electrons cannot move basically in gallium nitride, also in this one aluminum gallium nitride, and they behave like a 2D electron materials. They are in between the semiconductors basically. So we can use these materials and then also we can make this one, these sensors. And here we called field effect transistor. I think all you have studied in your BTech here how field effect transistor is called. And this is also one type of the field effector that we call the high electron mobility transistors, because these electrons mobility is very high. So we call this one is the high electron mobility transistors, but concept is same here. Here also on the gate, when we are applying the bias, this current is changing. Is clear? If you have any doubt in between, you can stop me and you can ask me. Okay, now how this is forming this one? Little bit we have to go in the deep basically to understand this one. So this is the conduction band is there. In the semiconductor we have the conduction band and valence band, this one. So in the conduction band, this is the aluminum gallium nitride here, conduction band. This is the gallium nitride, and when we are joining this one, because of this one spontaneous and piezoelectric basically nature of this materials here, we get the basically here particularly these electrons will capture here or will trap here. So you can see because at the room temperature we have some electrons, and now the minimum energy is here where these electrons will stay maximum time, wherever the energy is the minimum is there. Okay, so here is the minimum energy is there. So if you don't want to listen my talk, this one you will see it in the last row. Okay, because that is the minimum, you can't go outside this one. So similarly here, this is the minimum energy basically state is there. Okay, so here these electrons will trap. Now these electrons cannot move in this direction, they cannot move in this direction also, they can move in the third direction, in the Z direction. So now we can take the advantage of these materials basically in the third direction, we can make the source and drain, and we can make these high electron mobility transistors. So here because of the polarization, here you can visualize here these electrons are basically trapped at the heterojunction, and if you see the complete band diagram, this is the conduction band, this is the valence band, and now this 2D electron gas is forming at particular this region. So we can take the advantage of this confinement, and we can make the high electron mobility transistors. So here we have used this high electron mobility transistor, and then we have fabricated these devices. Now how to fabricate this one? We have to grow this one different layers, because gallium nitride substrates are not available, because when we melt the gallium nitride, before melting this start the decomposing. So we have to do some arrangement basically here, similar to basically different layer we have to grow. Stress management we have to do, because if defects are there, defects will capture these electrons. So we want basically almost defect free this one. And to grow this defect free, we have to grow these layers, and here we grow particularly, this is our, this one, hemp device is there. So here this is the, this TM transmission electron microscope images are there, and you can see these are the very thin layers basically here, how much thin we have to grow particularly, and these are grown on the basically 8-inch wafer at A Star Singapore, because MB this technique is very costly. Equipment cost is around 10 crore, and then again you need the accessory, so at least you need the 30 to 40 crores. But in Sri Pilani also, here they have basically this reactor, but we have grown at A Star and IIT Jodhpur, we are doing the fabrication. But in Sri Pilani, you can visit and you can see they have a very nice system for this growth of these materials. So we can grow the 8-inch wafer, and then basically we can make this one. Again, the mobility, how to measure basically, you have to do the Hall measurement. By using the Hall measurement, again you have to apply the magnetic field and electric field, and how much deflection is there, you can measure the by Hall effect, you can measure the mobility and carrier concentration. And during the growth, basically how much deflection is there, we have to do the in situ basically. This one is basically the deflection we need, because we have to do the lithography. So basically deflection growth here, because of the, there are two mismatch. One is the lattice constant mismatch here, because epithelial growth is there. Another one is the thermal lattice mismatch. That's because growth is taking place at more than 1050 degree. So when we are cooling, their stress is coming. So to minimize this one, we have to grow all these layers. So I think here how much quality is there, X-ray diffraction, this one is basically again RSM is there. So these layers are relaxed or not relaxed, we can measure this one. I think I can skip this one. These are the material characterizations, basically how to do the Raman spectroscopy. So by using this one, only we can confirm what is the quality of these layers are there. That means we need the minimum defects, otherwise these defects will kill our basically mobility. Okay, one thing is that we have grown basically high quality transistors. Now another this one, I think all you have heard this story basically, and today this is also valid in at least in the metro cities. By the bicycle you can reach faster than your car. Okay, so same is happening here. Okay, if your mobility is high, then also device is not okay, response is not fast basically. That means your device is not faster. So that means your car speed, okay, you are having OD or whatever high speed car is there, your speed is also decided by the signal. And what is signal here? Signal is your source and drain. How is your contact is there? Okay. So same basically here, okay, you have very good quality layer, but your source here is not forming the ohmic contacts basically. You are killing basically overall your speed of the your device. So first thing is that you have to make the ohmic contact basically, or your contact resistance should be minimum, this one. So here we have grown basically these materials, and we have optimized basically, okay, which material we have to deposit, not any metal, this one. We have to look for this one work function, and then we have to deposit. So we have deposited aluminum, chromium, and on the top basically is the gold is there, because gold will not allow to oxidize, otherwise aluminum and chromium will oxidize this one. So on the top we have to deposit the gold here, and we have to make this transmission line model TLM method. And by using this one, first we have to confirm this one our contact is having the minimum contact resistance or having the ohmic contact. So by using this one here model, here in between we have to measure basically spacing, we have to keep same, and from this law basically this equation we can measure contact resistance. So this is and how much is the basically this contact resistance, and your shunt resistance is there, seat resistance how much is there. So this should be the minimum. So we have optimized here, first thing is that this growth parameters we have optimized here, how much is the growth parameters are there. So what we have done this one, we have deposited aluminum, chromium and gold. So here you can see the thickness around 150 nanometer aluminum, 30 nanometer chromium and 200 nanometer the gold. So in the aluminum gallium nitride basically aluminum is diffusing. So we do the RTA. Through the RTA, this is the rapid thermal annealing is there. So we anneal our sample for 30 seconds at higher temperature around 850 or 900 at 50 degree for 60 seconds. So this aluminum is diffusing. Otherwise, if you do for the longer time, our metal contact will destroy this one. And then we deposit the here gate. Gate is the nickel. We need again the Schottky contact here. So nickel gold we deposit here, we need the ohmic contact, and this one is our device structure is there. So we have the source, drain, and here we have the gate particularly. So this is the our high, this one HEMT is there, high electron mobility transistor is there. And you can see yeah, here you can see basically the device, how we have fabricated, and we have isolated this one by the silicon nitride. Otherwise, what will happen when we put in the water, source and drain will short this one. So to do isolation, we deposit silicon nitride, and then on the top we deposit this gold basically gate electrode. Next here, this one is the basic device is the high electron mobility transistor. Now we have to functionalize basically this gate area, and then we have to make the we have to do the sensing measurement. So put our sensor inside the water, and then we detect basically how much change is there in the current basically, and this change in the current is related with the here how many this heavy metals are present. So first we have done the mercury, and for mercury we have used the 2D MOS to basically flex here, and then we have made basically these mercury sensor, because mercury is highly toxic basically, and many these chemical this textile industry in the pesticides also they use this mercury, and because of this one here in the food also they use the mercury, they do the coating this one. So how to detect this one, your food is safe, just we can put in the water and then we can check mercury is there or not. So in our lab regularly we grow basically these MOS to 2D layers by using the CVD methods. So we have the 3-zone CVD method, we have LPCVD, also we have thermal CVD. So in the LPCVD we take the moly and sulfur precursor, and then reaction is happening. Here we use the solid sources, but we cannot use this one here because these MOS2 flakes, they are growing at the higher temperature around 850 degree centigrades, and because we have already fabricated source and drain, now we cannot heat for 850 degree centigrades. So we have to look for a low method, or we have to transfer from here to basically on our device, because this grow temperature is very high. So here we use this one hydrothermal, that is the low temperature method is there, and then we get basically we use MO3 and thiourea, and these are the optimized parameter is there, and we get basically these 2D flex. So first what we have to do this one, we have to characterize these materials. So by Raman spectroscopy and X-ray diffraction, we have characterized this one, and we found this grown material is there. This one is the MO2 is there, because we have used the thiourea and MO3. We have not found any peak corresponding to these materials. That means this reaction was successful. So this reaction was successful. Another, how is the surface morphology? So you can see in the electron microscope, these are very nice flakes, and if you have more surface area, because here reaction is depending on the your chemical reaction is their surface area based. So if you have more surface area, we can get the higher sensitivity. So surface area is very high. Next, what we have done, we have fabricated this one device, we have mixed with IPA this one, and then we have basically transferred on the gate. So here is the this 2D MOS2 flex, and we have the source and drain. So this is our final device is there. And you can see some photographs where you can see this one, how we are fabricating this one, and you can see some this one closer look. And after this one here drop cast, you can see this MOS2 flex are they are uniformly distributed on this one. And again we have done, after transferring this one, we have done AFM and this one here electron microscopy, and we have confirmed this one our 2D material is successfully basically transferred on the gate region. Then we have done the measurements here. So we put basically here our device inside this one, and what we do, we apply basically some constant here voltage between source and drain. So we apply 0.5 volt here that we have optimized, where we are getting the maximum change in the current, and then we monitor the drain current. And what we are doing, we are putting here basically different concentration. We are putting the different concentration particularly in this one, and now how this current is changing with different concentration. So here you can see when this one, even not because defined limit is the ppb is there, 1 ppb, even we can measure in the ppt also this one. So because here this 2D electron gas is there, this is highly sensitive to the surface. So if even very small amount of mercury is coming, that is also we can detect this one. So here this is the real time monitoring is there. When we are mixing, basically this one is changing. Initially some change is positive, then here at higher concentration this one is the in the here current started decreasing. So we have proposed the mechanism, and this paper is in sensor and aquators B. Initially there are some surface here on the MOS2 negative charges, and now mercury here bond is happening, because of this one current is increasing, and then we started the decreasing this one here. Another important parameter is the cross selectivity. Suppose there are other ions, so we have done basically in the different ions. Also we mix all ions, and then we have done the measurements, and we found the almost same change in the current here. Whatever we got with the mercury, that shows this sensor is highly selective towards the mercury ions. And here sensitivity, here these are the parameter, around 0.6 microampere current change is there with ppb this one, so that easily we can detect. And another in the sensors important parameter is there, that is the transfer function, because your output signal is the some electrical signal is there, and here is the current is there. Now when you are changing your concentration, what is the relation between your input and output? If this is a linear function, your transfer function is linear. So when we calibrate, basically we need the less number of points here, 1-2 points. So up to 100 this one ppb, this is the linear, and that is the basically if 100 ppb is there, that means it's very high. Water is not drinkable. Even above 1 ppb is also not drinkable. So we can get, if this current is increasing above this one here, that water is not safe particularly. So we here again we have optimized how much amount of MOS2 we have to load this one, and we found this one around 20 milligram per milliliter is sufficient, because when we are increasing then is also not much change is there. So at least we have to use this one here around 20 milligram per milliliter. Again, you have seen in the water purifiers, basically we have the UV lamp to kill the bacteria. This one, some biological here, these bacteria. So again, if we put our sensor near to this one, what is happening? And we found when we are doing the measurement, our sensor is here. When we are doing the measurements under the UV lamp, basically our sensitivity is improved. Here you can see even we can measure in the PPT. In the previous case only PPB we were able to measure, not in the PPT, but here we can measure in PPT range also. So range also we have increased, and if we see around the sensing response here, sensitivity we have improved by 850 times just by putting this one, mounting this sensor near to the UV lamp we have to use to kill the bacteria, or this one in the reverse we can use this UV source and then we can do this one. So by the here photo activation we can improve their sensitivity. So that means here, if you are improving the conductivity with the photon, what is happening? Your MOS2 materials conductivity is improving. So we thought this one by other way, can we improve this one? So MOS2 exists in the two phases. One is the semiconducting phase, another one is the metallic phase is there. So we have taken the mixed this one, metallic and semiconducting, and then we have studies what will happen, because 1T phase here conductivity is very high. So again we have done these measurements basically, and again one more here we have applied the intentionally some biasing. In the previous case we have not applying the this one gate biasing. So we have optimized all these parameters, and we found this one we can improve basically 520 times just by mixing with some 1T here in the 2H phase. And again we can improve 850 times just by applying some gate bias. So these are the ways basically to improve the sensor performance. This one, how we can improve the sensor's performance. So if conductivity is improving, then we have used the AG nanowires intentionally, and then we put on the basically this region here, this MOS2 and AG paste. Here we have varied the ratio, but this ratio gave the maximum basically response, and we found in this case our current is in the milliamperes. So around 2500 times we can improve this one MOS2 sensitivity just by mixing the this one here silver nanowires, and we can improve 3 times this here just putting these silver nanowires as compared to the UV this one, because by UV also we have improved. So if intentionally if we can mix MOS2 with some conducting materials, we can improve basically their sensitivity. Another here we have tried this one for the lead, because in the Jodhpur and Pali region, that is the textile area is there, and you can see the current situation how they are releasing these water without any treatment this one. So can we develop some sensor to monitor at least this textile industry water this one? So here we have used another 2D materials. This is this graphitic carbon nitride is there. Again this is the structure is the again these are in the 2D nano sheets. We have synthesized this one and we have transferred basically on the gate here, and we found this one here. You can see basically there is a change in the current here 1 ppb, because here limit is the 5 ppb. So easily this is the blank here. It's in the DI water how much is there, and then we are mixing this one. So easily we can see the change in the current IDS, and this change basically we can relate with the concentration. And we found from the other ions we have tried whatever is possible in the lab, almost all heavy metals, and we found this sensor is highly selective towards the lead. Here one thing is there, pH is also playing, so we have to integrate with pH and then we have to get the actual concentration, how much concentration is there. And we propose the mechanism here. What is happening when these ions, they are absorbing the lead ions. Basically, this 2D electron gas density is there. This one is changing because the drain current is there. That is decided by the basically how much 2D electron this density is there. We have tested in the Jodhpur, we have the Kalana lake, we get the water from the Punjab, this one. So we have taken the samples and then we have tested and we found that water is the drinkable, that is not basically destroyed by any this industry, this one, because directly we are getting this one. So we have mixed around 10 ppb level and then we have measured this one, and this intensely we have measured. This one is our DI water and this one is the Kalana, this one lake water is there. So this is safe to drink basically, this water. Again we are trying for arsenic. Here we are using basically this SNS2, another 2D material is there. These are the material characterizations, and then we have done the arsenic ions basically, and here you can see we can detect even low concentration 10 ppb, because here arsenic concentration is higher, this one. So by using this one basically we can make the arsenic, and this work is under progress. We are doing some more measurements here, repeatability and other data basically. Next, once your device is ready, your sensor is not ready because you need the complete module basically. Your output should come in the some numbers, otherwise this is not complete. So here we have made basically this complete here this basically circuit. So this IC is designed by our collaborator from the Edinburgh University here. And here what is happening basically, when this current, there is a current change, we are converting in the delay time here, and this from the delay time here because we are applying the pulse, and in the pulse how much delay is there, this is related with the change in the current, and change in the current is related with the basically your ion concentration. So we have done this one, and then we have this one, analog to digital converter basically, and we can get the number. So here you can see the actual how we have connected particularly this one. This IC is mainly is manufactured by the TSMC, but this was designed by the here our collaborator group from Edinburgh University. And then we have done, this is the our sensor response. We measure by using the our Kitle source here, this 4200, and then we have measured the delay time in microsecond. Its behavior is almost same, and then we have measured basically our this one time, this one domain output, how the decimal equivalent delay is there, and this number is almost in the same nature. Whatever this is difference is there, that we can compensate, this one we can make basically. So here we have designed the complete basically sensor setup from the readout circuit, from the device, and then basically we can make this one. So our future plan is there to make for few more basically this one cadmium and this one antimony and TDS, and to combine all this one, and then here we want to install in the water purifier. So in the display you can see now, because this cartridge life is depending on the based on the time. They have some time basically, okay, 100 hours or 500 hours this one. And if your cartridge, okay, you get the satisfaction, I have replaced the cartridge, but actually you don't know your water is this one, you are getting purified or not, this one particularly. So this we can use these sensors for online monitoring, this one. And another work I will come this one, because many of this one PhD student, they are working on the gas sensors, this one. So here we do the gas sensor, but we don't measure basically by the this one source meters. Here we make the complete system. So we use this one impedance analyzer here. We make our sensor, complete sensor. On this one we deposit basically, and we have this one constant bias we apply for the heater. Then we have MFC, and through the laptop we control. So this one is much cheaper than the whatever we are doing, because your 45 lakh rupees you have to spend for 4200, but here is only in the few thousands basically we can buy all this one and we can get this data. So here you can see with impedance, because baseline is the problem in the sensors. If today you are doing, your baseline is resistance is different. If you are doing 5 days, your baseline will shift this one. So how to overcome this problem? So we have done the impedance basically, and you can see here baseline is the problem, but when we are increasing the frequency, when we are measuring here, baseline is almost constant. So we can measure at the different frequency basically, we can optimize the frequency for the sensor, and then we can measure the impedance here. So not only the here impedance, we can take the phase change degree, we can take the real part, we can take the imaginary part, and then we can apply the our this one artificial algorithms, ML algorithms. So here you can see at different ppm, this is the actual data by the sensor we are getting, this is by the we are controlling the gaze basically. So this one is the here by the gaze, this one is the sensor data, and this is the detected data here. So at same z, theta, here 4 parameters simultaneously we can measure. And now what we are doing here, we are applying this one artificial neural network. So here our output is there. Basically here we use how much input is there, some training data we call this one. So from the 30% our training data, our algorithm is getting trained basically what should be the output. So output there are this one mathematical equations basically, and from this one our output, because initially we are giving the output and input, and now this algorithm basically is forming, and from this one we get this one. So you can see here we have done with the humidity. So initial two data we have used as a training purpose. Suppose we are using humidity 20% or dry air, and then here we have not used basically. So you can see this one here we got this black one is the predicted data is there. So almost we are reaching close to the actual data this one. So by using the 20% basically 30% training data here, we can basically here is the 40% because we have measured total 5 and we have given the 2 inputs this one. So by giving the 40% basically here training data here, we can predict basically what will be the response this one. Again we have used the single frequency. This is the single frequency. We can use the multiple frequency. When you are using the multiple here multi-frequency model basically, here we are close to the actual data, because initial sensor is taking some time basically to woke up basically, but that we can overcome basically by using the multi-frequency. So this is the another way basically how we can use the this machine learning and AI algorithms basically in the sensors to make the decision to predict this one what will be the your actual output, because when we are doing the analog always some error is there, but if we can apply basically these models basically we can predict this data. So I would like to summarize. I think last few rows they are not understanding or they are not much interested this one. So okay, we have fabricated. I think this device is new for you, this one. Yeah, definitely this one is new for the bachelor students, but if you plan for research basically, you can think how we can use basically these transistors. Concept is same this one, but you can make the new devices. So we have made here sensors using the same your field effect transistor that we call the high electron mobility transistor is there, and we have made the complete system. We have improved this one selectivity, sensitivity, other parameters just by playing the some fundamental aspects by improving the conductivity using the photo this one. And this work started by the others, now Nipun is continuing, and I would like to thank Sudhir Ranjan Tripathi who provided us the wafers from Singapore, because this growth is again the complicated metals we can use 1D also. Yes, another difficulty is there from the single nanowire handling, that is not easy, because when we are going for the large scale production, that is the problem. But here we can do the large scale just by, because we are doing by this one spin coating we can do on many devices this one. But in the CNT we can use the mixer, okay, but CNT, because first we have to buy some simulation, or by the literature we have to find can carbon nanotube can absorb some ion or not, because here MOS2 is absorbing this one mercury ions. The mobility will be better. Mobility will be better, but that is not detecting. Yes, that is the problem. Yeah. So we have to see also the basically not only the mobility. Mobility is okay, is one aspect is there in the transistors, but here in the sensors basically is required is that particular material is absorbing a targeted your materials or not.
In one XRD, I have also seen that there are 4 quadrants, 0002.
Yes.
So what is the fourth one?
Oh, that one is in the hexagonal. So one is A, B, and C is there generally, but third they use A plus B.
Okay.
Yeah, yeah, minus this one. A plus B and minus, that one is the fourth in the hexagonals, this one. Yes. So that is the culture basically, in how to represent this one hexagonal material.
So my question is that in transistor family we have a JFET, we have a MOSFET,
yes,
we have a CMOS, so many families there. Why you are talking only about the JFETs here? Junction field effect transistor.
Yes, yes, yes.
Other transistor we can't use for this experiment?
No, what is the problem? Because mostly these are silicon based. So when we are putting this one silicon in the water, one problem is their oxidize basically, will make the SiO2. Another problem is there because the 2D electron gas, as I said, in the junction field effect, that width is there, that one is the large. So if small changes, because ions, these are in the PBB. So we require large change, definitely we can measure, but not small change. Because here 2D electron gas is there, that is totally is depending on the surface states. So small amount also we can measure by using high electron mobility transistors, and mobility is high. Yes, because here is forming your channel only in 5 nanometers. Their channel is 50 nanometer or yeah. So that is the problem. So in the 50 nanometer is 1 nanometer is plus minus, nothing will change. This is similar. For example, Ambani will give you 10 crore rupees. Ambani is nothing will change, na? Because he is rich, this one. But if you give, for example, 50 lakh rupees, your lifestyle will change.
No,
So that we are measuring, no, that is the thickness basically, because there is the 50 nanometer channel.
the thing is that being as a teacher, we are talking that JFET is outdated.
Yes.
Normally, when we are teaching, I am professor in the HM College of Engineering.
Okay.
We are saying that, okay, this is the drawback of JFET that we are going to use.
No, that is outdated only in silicon, no, not everywhere.
But here, we can use that.
Yes. So that is only in the when we are going in the silicon technology is outdated, because CMOS and other, they have the logic circuit and everything we are fabricating. But here we can use this one. Okay. So
Student must know.
yes. So here we are using the simple concept, this one. Yes.
Thank you, sir.
Yeah. Yeah, that's why in the semiconductors always we talk about the minority carriers, because change, we want to see change where change is high. Okay. So change, because we are using the semiconductor here, or we are using the very thin, because here if small change is there, we can easily measure. So suppose you will get 10 crores, next day you will come in a car basically, but Ambani will come in the same car. Because, so that's why here we use in the MOS2 also semiconducting phase, not metallic phase. Because in the majorities, change is negligible.
So have you done any stability measurement for the MOS2, because it's a very highly unstable material when you are growing it by simply drop costing and all.
Yes.
So what about its adhesion and stability or gate behavior?
Yeah, so that we do some thermal treatment basically. Yeah, we do thermal treatment, how much amount that we have optimized basically, how much we have to load basically amount. So we have to heat, otherwise this adhesion is poor particularly.
Yeah, basically adhesion.
Yes.
And what will be the tentative features for the machine learning tentative features of the sensing?
Features, one thing, this one is taking from the response also, how much phase is there, because otherwise we have only resistance, this one. Now with frequency, that response is also changing. That your response time is there at different frequencies different. So machine learning is getting more basically data, training data.
So what kind of training data? I mean, data is related to the device structure?
Yeah, device.
Device structure.
Yeah, device structure. So basically that is the black box, basically machine learning. Output, where is the minimum error is there. Yeah.
That's nice. Very good.
And because we have to do that in the same condition, we have to do the measurements. So here you have seen this one. We have made the complete sensor and complete sensing module. And we are not using semiconductor analyzer because we cannot take this much data. So here we use this analog basically. And then,
just in order to generate different features.
yeah, different features. We need more data.
Yeah, more data.
Yeah, yes, because otherwise you have 5 or 10 cycles you can take by this one. Here we use 1,000 data basically. Yes.
As the data set is used,
Yeah, so yes, more accurate. Otherwise, from the two data we are giving, and then yeah, that is not possible.
unreliable model.
Yes, yes. That's why if you see this one, now we are doing with temperature also, we are playing this one. Here temperature, you can see how, these are the different ppm here. So we are doing different ppm, frequency is this one, phase also, this one, humidity also. And now with temperature also we are playing this one. Because we need some fast, basically this one, our temperature controller that can change the temperature, different temperature.
And have you also done any durability tests, like the measurement of sensing?
Yes, so these are taking the months basically. This one is the complete basically on the sensor. We fabricate by the sputtering. These are done by the sputtering, and we deposit here basically. So now we do the wire bonding, everything. This tube we make in the lab. This one, because we do initial some measurements we do on the chip basically, and once we got okay this material is stable, then we have to go for this. Yeah, any questions? Yes. Yeah, mainly for PhD students, because now AI and ML is everywhere. So you guys, you have to use this
Very interesting. That may be very interesting for you.
Yeah.
Thank you very much, sir. Thank you, sir, for gracing us your presence and knowledgeable insights. We are truly honored to have you as a part of our ATAL-FDP. Now, I would like to request Dr. Dhiren Singh, Professor Triple ED BITS Pilani, to kindly honor our guest speaker with the token of love. Thank you, sir.